Okay, so good morning everyone, and today we continue discussing electrical current, and we consider direct current. And I would like to solve problem number 464. Well, it says that we have such an electric circuit consisting of 3 resistors, and these resistors are equal, they are identical. Each has a resistance R, and we have to find the resistance between points A and B if there is such a connection in this circuit. This point is connected by a wire with this point, and this point is connected by a wire with this point. So we have to find the resistance of such a connection of resistors. We have to find resistance between points A and B. Well, in order to solve this problem, we have to figure out what is this connection, whether the connection is a series or a parallel connection. Well, first of all, we note that point A is connected with this point, which I will denote as A prime. As these points are connected by a conducting wire, then the potential in these points A and A prime is the same. The same potential, it means that there is no potential difference between these 2 points. It means that this point A and A prime is actually a single point, and I will denote it as a single point A. And the two resistors are connected in such a way that each resistor is connected by one of its terminals to this point A, so one terminal of each resistor is connected to this point A, which is the same as A prime, and another connector of each resistor is connected to point B prime, which is the same as point B. The point B prime has the same potential as point B because this is a conducting wire. So another end of each resistor is connected to this point B. This is the point B. So the equivalent scheme for the first 2 resistors will be as shown on this sketch. Now what about the last resistor? By one of its ends, by one of its terminals, it's connected to point B. So I will show this connection in this way. This is the last resistor. And the other terminal of this resistor is connected to point A. That's it. It's connected to point A. So the equivalent scheme of the original scheme, it turns out to be just a parallel connection of 3 resistors. Therefore, the resistance between points A and B will be equal to R divided by 3, because 3 identical resistors are connected here. And the general formula would be 1 divided by the unknown resistance between points A and B. And here we will have 1 over R plus 1 over R plus 1 over R. That is 3 over R. That is the general formula for the parallel connection of 3 resistors. So the answer is found in such a simple way, and the most important point in this problem is to guess that such connection of resistors is actually a parallel connection. Suppose we disconnect this first wire and disconnect the second wire. Then the total resistance of this serial series connection, connection in series, will be 3R. In this case, that will be 3R, the total resistance, if the two wires are disconnected. So by connecting and disconnecting these wires, we may switch the total resistance between 3R and R divided by 3. And disconnecting can be realized by a switch. So by switching this key, also it may be called a key, switching the key, that is short-circuiting the contacts, we will switch between the two different values of a resistance between points A and B. Such is the analysis of problem 464. Next, we will consider problem 466. Well, it says, find the resistance of a wire cube when it is connected to a circuit between points A and B. And I will show these points on the graph. The resistance of each edge of the cube is R. So we have a wire cube, something like that. We have a cube made of wire. These are all elements of conducting wire, and each element has a resistance R. And this section and this edge of the cube and this edge, all the edges have the same resistance R, because these are identical pieces of wire. And the cube is connected to the external circuit by the contacts in point A and point B. That is, we have to find the resistance of such a wire cube between points A and B. So the question is the same as in the previous problem. We have to find the resistance of a wire cube in such a circuit between points A and B. Well, such a three-dimensional circuit seems to be neither parallel nor series connection of resistors, but anyway, it's possible to simplify this scheme and to draw an equivalent scheme, something like what we have done in the previous problem. It's possible to draw an equivalent scheme here if we consider carefully the potentials in different points of this cube. Imagine we apply an external voltage, plus and minus. We apply an external source of voltage. Then there will be a current flowing here through the edges of this cube. And we will find that this vertices, this point, has some potential, which differs from the potential of point A, but this point will have the same potential because its position in the scheme is the same. And also there is another point, this one, which will have the same potential. So these 3 points of the scheme will have the same electrical potential. Therefore, the potential difference between these 3 points is 0. It means that if we connect all these 3 points by some conducting wire, then there will be no current flowing between these points through the new connecting wire. Therefore, the first 3 resistors, the first 3 sections of this cube can be depicted on an equivalent scheme like 3 parallel resistors. All of them equal. All of them equal. And this is point A. Point A starting at this point. and all the resistors are equal to R, all of them are identical, and all of them will have the same potential at an opposite connection, at an opposite end of each section will have the same potential. It means that we may connect all these points, all these cube vertices, the three cube vertices may be connected, and nothing will be changed in this scheme because the current will not go through this wire, because the electrical potential of these points is the same, and therefore if we connect these points by a wire, nothing will change. The electrical potentials will not change after connection. In the same way, we can treat the cube edges originating from point B, that is this resistor and this one, because all these 3 points will have the same electrical potential. Points, I will denote them by some sign. All these points will have equal or the same electrical potential. In this, therefore, all these 3 resistors can also be considered as connected in parallel. And this is point B of the cube. And all the resistors are the same. So we have dealt with the 3 vertices and another 3 vertices and another 3 edges of the cube, this one and this one and this one. And so what remains here, this one and that one and this one and another one and this one and this one. So how many? 1, 2, 3, 4, 5, 6. Another 3 edges, another 6 edges of the cube are here. But if we look at any such resistor, any one of the remaining 6 resistors, we will discover that the potential difference on each resistor is the same, because this point has the same potential, the same electrical potential as this point. We have discovered it. And this point has the same potential as this point. So the potential difference on this section of the cube will be the same as the potential difference on this section of the cube, and the same as the potential difference on this section, etc., etc. So the remaining 6 sections of the cube can be presented like 6 resistors connected in parallel with each other, and all of them are identical, and each resistor has a resistance R. So these are the 6 resistors of the intermediate edges, intermediate sections of the cube, which are located between the originally considered 3 points having the same electrical potential and finally considered 3 vertices having again equal electrical potential. So, recalling this fact that the potential difference on each of these 6 resistors is the same, we may conclude that such will be the equivalent scheme where the potential difference on all these 6 resistors is the same. So now after composing such an equivalent scheme of the cube made of wire, we may easily calculate the resistance between point A and B. That will be the resistance of the first section of 3 resistors connected in parallel. That will be R divided by 3. We have considered such situation in the previous problem. And the same resistance will be here, again, R divided by 3. That is the total resistance of this section. And here will be the resistance of this middle section, medium section, will be R divided by 6. So the total resistance between points R and B will be R divided by 3 plus r divided by 6 and plus r over 3. That will be 2 divided by 6 and 2 divided by 6. That will be 4 plus 1, that is 5 r divided by 6. That will be the total resistance of a wire cube, the resistance measured between points A and B. The opposite vertices of the cube, which belong to a diagonal, the cube diagonal. Such is the solution of this problem. First step, we have to figure out what may be the equivalent scheme of a wire cube. And we find the equivalent scheme based on consideration of different potential differences on various sections of this cube. And after we have figured out and composed and drawn this equivalent scheme, then it's very easy to calculate the resistance of some resistors in parallel and 3 sections in series. So as these 3 sections are connected in series, we have to add the resistances of these 3 different sections. Now I will consider solution of problem number 470. Problem 470 deals with an infinite circuit between points A and B. There is an infinite circuit consisting of similar elements of similar cells. So this one single cell is similar to the next cell and similar to the next cell, and etc. And finally we will have the final cell here. So there is an infinite number of similar cells, and all the resistors are identical. All the resistors have the same resistance. Let's consider this problem in such a formulation, that all the resistors are similar. And this is an infinite cell. What is an infinite in physical sense of the word? It means that the circuit is certainly finite. Certainly there is a finite number of cells, but a very large number of cells, maybe 100, maybe 200, maybe 1000. So we have to find the resistance between points A and B. And if this circuit is infinite, or very large number of cells in it, it's obvious that if we connect an additional cell here, an additional circuit, then nothing will change. If there were 2000 such cells and we connect just another one, number 2001, then nothing will change, and the resistance between points A and B will not change, because the difference is very small between very large number of cells and very large plus 1. That's practically the same. So the resistance between these 2 points will not change. And it means that the resistance between these 2 points will be the same as the resistance between these 2 points, A prime and B prime. If I disconnect this circuit here, if I disconnect it, and measure the resistance of the remaining circuit between points A prime and B prime, its resistance will be the same as the resistance of the original circuit when the first cell is connected. So I may consider two situations. When the first cell is disconnected and I have to measure the resistance between A prime and B prime, the resistance of the remaining circuit. And the second situation when this first cell here is connected and I have to measure the resistance between points A and B. It's obvious that if this circuit is very large, well, practically infinite, then the resistance of the infinite circuit between points A and B will be the same as the resistance between A prime and B prime if the first cell is disconnected. That means that all this circuit here, all this one, has the resistance between points A and B, which is equal to RAB. The resistance here of the remaining circuit is the same as the resistance of the original circuit. And that means that we can calculate this resistance easily just considering the first cell of this circuit. I will denote this resistance by X because we have to find it. We have to find this unknown quantity. So in this connection, we know that point A and point B may be presented in the following way: the first resistance and the second and another one, and here is the resistance X, which represents the remaining part of the circuit between points A prime and B prime. This single resistor is the resistance of the remaining infinite circuit, the resistance between points A prime and B prime if the first cell is disconnected. That is, the single unknown resistor represents the infinite circuit here. And we know that the resistance between points A and B is also X. So it's easy to calculate the resistance of this remaining circuit. We have parallel connection of resistor R, this one, and 3 other resistors, one of which is X. So for parallel connection, we may use this very well-known formula for the resistance in parallel connection. That will be 1 over R, that is the resistance of first branch in this parallel connection, and plus 1 divided by the resistance of the second branch, which will be 2R plus X, because these 3 resistors in the second branch, these 3 resistors are connected in series. So in order to find the resistance of the second branch, we have to add all the 3 resistors. We will obtain 2R plus X. And this part of the circuit will be connected in parallel with the first resistor R. So the total resistance will be found by solving this equation with respect to X. Well, let us solve this equation. Let us solve it. It will be what? 1 divided by X will be equal to R times 2R plus X in denominator, and in the numerator we will have 2R plus X plus R. That will be 3R plus X divided by R, 2R plus X. And now by multiplying all this equation through multiplying by X and also multiplying by this denominator, we will come to the following equation. First, this denominator will be found on the left-hand side of the equation, that is 2R plus X. And now the right-hand side will be equal to X multiplied by 3R plus X. So that will be 2r squared plus xr. And in another part of the equation, we will find it as x squared plus 3xr. So these are similar terms. These are the similar terms, if I have not mistaken. These are similar terms, and the equation may be rewritten as x squared plus 3 minus 1, that will be 2xr, and minus 2r squared, that will be 0. And to find the solution of this quadratic equation, we need to know the formula for the roots of quadratic equation, and that will be the unknown quantity x will be equal to minus this coefficient 2r divided by 2, that will be minus r, plus minus something else. But if I choose the sign minus here, I will obtain obviously a negative quantity. A negative quantity for the resistance is unphysical, it should be excluded. We don't consider negative quantities, we consider only normal positive resistance. So I must choose only the positive sign here and omit the negative sign. We don't consider negative quantities for the resistance. So I choose only the positive sign, and that will be a square root of this quantity r squared minus this term that will give us now plus 2r squared. Yes, and that will give us minus r plus r square root of 1 plus 2, which is 3. Now the unknown quantity x may be written finally as r times square root of 3 minus 1. That's it. That's the unknown resistance between points A and B in such an infinite or very large, very long circuit consisting of many, many identical cells. And it's obvious that if we have a very long circuit consisting of hundreds and maybe thousands of such cells, it's obvious that if we disconnect the first cell consisting of these 3 resistors, then the remaining circuit between points A prime and B prime will have the same resistance. It will not change because the number of cells is very large. It's almost infinite. It's very large. So this is the main idea for solving such a problem. This is the main idea. So that will be the resistance. X is the resistance between points A and B for such a very long circuit consisting of a very large number of identical cells. Now let's consider another problem, which will be 460. Problem 460 says, what resistance R should be used to shunt a galvanometer with an internal resistance of capital R equal to 10 kilo ohm. What resistance R should be used to shunt such a galvanometer to reduce its sensitivity by 50 times, by n times n equal to 50. So we have a galvanometer. A galvanometer is a device designed to measure electrical current. So this is a device which measures electrical current, which flows here. So we have to shunt this galvanometer. What does it mean to shunt? It means to connect another resistance in parallel to this galvanometer, in parallel, so that this additional resistance will take some current and therefore reduce the current that goes through the galvanometer. And such an additional resistor is called a shunt, and such a procedure of attaching this shunt in order to reduce the sensitivity of the galvanometer, such a procedure is called shunting. So we have to shunt the galvanometer in order to reduce its sensitivity by 50 times. If we know that the internal resistance of galvanometer is given, it's 10 kiloohms, so we may imagine this like an internal resistance. We may show it here. This is the internal resistance inside this device, the resistance of its internal circuit. So if there is no shunt at all, then we don't pay attention to this circuit, and we know that there is a current I, the electrical current, which goes in this direction and goes through the galvanometer, and galvanometer shows this current. It measures this current. And let this original current be denoted by E0. In this case, if no shunt is attached here, the galvanometer will measure this I0 current. If we attach the shunt, then the current which will go through the galvanometer will be different, because part of the current will go through the shunt. Some current I2 will go through the shunt, and another current I1 will go through the galvanometer. Due to the law of conservation of electric charges, we know that the total current which goes through this wire will be equal to I1 plus I2. The total current coming to this point will be equal to the total current leaving this point, because no charge can be accumulated here at this point. So that the sum of these two charges is equal to the total charge here. Now the galvanometer will measure the current I1. And we know that this current, according to the statement of the problem, must be 50 times smaller than the input current I0. So this current which goes through the galvanometer must be the input current I0 divided by 50. Okay, let's put it like divided by n. We know that n is the number which is used to reduce the sensitivity of galvanometer, to reduce the sensitivity. So what does it mean to reduce the sensitivity? It means that suppose the galvanometer can measure the maximum possible current I0, maximum possible current, which means that the device arrow will show the maximum possible number on the scale. It will have the maximum allowed reading of this device. That will be I0. Then, after shunting, the same input current will result in n times smaller current flowing through the galvanometer, and so the readings of this device will be n times smaller, which means that the device will have a reduced sensibility, a reduced sensitivity. It will have a reduced reading under the same input current which is coming here. So, and in this situation, when we have shunt the galvanometer, the maximum allowed current which will be measured will be 50 times or n times larger than without the shunt. So how can we calculate these currents I1 and I2, and how can we relate these currents with the given internal resistance of the galvanometer and the unknown resistance R, which we have to find in this problem? Well, the potential difference between these 2 points must be the same and independent on how we calculate this potential difference, whether we measure the potential difference along this circuit or we measure the potential difference along this circuit element, along this section. So if we consider current I1, then the potential difference on the galvanometer will be equal to I1 times capital R. But if we measure the same potential difference considering current I2 and the lower section in this circuit, then the same potential difference between these 2 points will be equal to I2 times small r, the resistance of the shunt. So we have all the necessary physical laws, all the necessary equations to calculate the unknown resistance R. Let's immediately start calculating it. R will be equal to capital R, I1 divided by I2. And I1 can be calculated using this formula. So we will have capital R, and instead of I1, I use this expression, which will be I0 divided by N and divided by I2. And then we have somehow to finish this calculation, we have to somehow deal with these 2 currents which are unknown. So we may use the first equation or we may use this equation to substitute I2 from here into this formula, and that will give us I0 divided by N, and instead of I2 I will put I0 minus I1. And now by dividing this formula by I0, I will obtain something interesting. That will be 1 divided by N, and if I divide this round bracket by I0, I will obtain a unit minus I1 divided by I0. Why is it convenient to do such an operation, to divide this by I0? Because I1 divided by I0 is actually known to us. From here we can easily obtain that I1 divided by I0 is 1 divided by N. So this expression is known, and the total formula will give us R divided by N, and here we will have 1 divided minus 1 divided by N. After opening these brackets, I will obtain the final answer, which will be capital R divided by N minus 1. Such will be the resistance of the shunt, which is necessary to reduce the sensitivity of this device by N times. We are given the resistance and the N, it's known, so I will continue calculations here. The resistance is 10 kilo ohm, that is 10,000 ohm, divided by N, which is 50, and minus 1, which is 49. So this expression will give you something. If we divide by 50, dividing by 49 is almost like dividing by 50. If we divide by 50, we will obtain something like 200. So about 200 ohms, that must be the resistance of the shunt to be used in this scheme in order to reduce the sensitivity of the device by 50 times. About 200 ohms. About 200 ohm. Actually, if we divide by 49 rather than by 50, we will obtain a slightly larger resistance, but it makes no sense to be so in such a way so strict in our calculations. It doesn't matter if we choose 200 ohms or another resistance just 2% larger. The difference will be just 2%. If I choose dividing by 50 or dividing by 49, the difference is just 2%. So the 2% of 200 is 4. So I may obtain 204 probably if I divide something like approximately. It doesn't matter if I take 200 ohms or 204 ohm resistor. It doesn't matter. Practically, it will reduce the sensitivity by about 50 times. That's enough to give the answer to this problem. So a shunt is used to reduce the current which flows through the device, because the shunt will take some portion of the current and some portion, a good portion of the current. Well, it's 98% of the current will flow through a different circuit rather than through the device. So a larger portion of current will go here to shunt the device, and the device sensitivity will be reduced. That's the main idea behind using shunts. The next thing I would like to consider will be some theoretical issues rather than practical problems. I will consider the Ohm's law for a closed circuit. The Ohm's law for a closed circuit. So imagine some closed circuit which consists of a voltage source which creates a voltage on its connectors, and this voltage source, as it is usually the case, has some internal resistance. So this internal resistance can be shown here as some internal resistance of this voltage source. And so this is the device, which is the battery, creating some voltage, including the internal resistance, which I'm just showing separately because it's the most convenient way to show the internal resistance, rather than drawing this small resistance inside. It's by convention, we show this internal resistance just close to this battery, and this battery is connected to some external resistor, R, and we have to derive the Ohm's law for such a closed circuit. So the current, the electrical current, will flow from plus connector to minus connector, that is in this direction. That will be the current flowing in this circuit. If there is a current, then there will be a potential difference between these 2 points, points A and B, and the potential difference between A and B will be equal, due to Ohm's law, the strength of the electric current times the resistance of this resistor. So that will be the potential difference between points A and B. If we recall what is the potential difference by definition, that is a work which is produced by the electric field if a unit charge is carried from point A to point B. So we may take a small charge, delta Q, and carry it from point A to point B. While we carry the charge along the conducting wire, we produce no work and the field produces no work because the conducting wire has the same potential and the potential difference between different points of the wire is zero. But when the charge goes through the resistor, then there is some potential difference, which is UAB, potential difference between the contacts of this resistor, and the small charge flowing through the resistor will require some work to be produced. The electric field will produce some work when this charge goes through the resistor, because the charge is normally chosen a positive, small positive charge, and the electric field flows from positive sign to negative contact, from positive to negative contacts of the battery. So this is a small positive charge, and when it goes through the resistor, it will be repulsed from the left contact of this resistor and attracted to the right contact, because these contacts have positive and negative charges. And so that in this way the electric field will produce some work when this charge is carried through the resistor. And this work delta A produced when the small charge delta Q is carried here. The larger the charge, the larger will be the work, but the ratio of work produced to the amount of charge will be equal to the potential difference by definition. This is the definition of potential difference in physics for electrical fields. This is the definition, this is not the physics law. This is the definition of this quantity, potential difference. And as we have defined this potential difference in this way, then we may obtain the physics law, which is the Ohm's law, which has been originally obtained experimentally. It was experimentally discovered that the potential difference is proportional to the electric current flowing here and to the resistance of the chosen resistor. So this is an experimentally established law, originally established experimentally, and later it was derived both in classical physics, in classical electron theory, and in quantum physics. Using Schrödinger equation, it's possible to obtain the Ohm's law both in classical and in quantum approaches. But this is a physics law obtained after we have defined this quantity, a potential difference, in this way. So we know that the potential difference is some work, and the ratio of work to the charge being carried here. So the work done by the electric field to carry this charge along the closed circuit, the work, we may naturally ask a question: what will be the work of electric field needed to carry this charge through the closed circuit from point A around the circuit and to return to point A? So if the small charge is carried around the circuit from point A and return to the same point A, what will be the work done by the electric field? Well, if there were some positive work, then the electric charge going here, the electric current moving in this closed circuit, will produce some positive work, and that would be a perpetuum mobile. That would be a violation of the law of conservation of energy. If we obtain work from nothing, just obtain it, then that would be a violation of the law of conservation of energy. And due to the law of conservation of energy, we know that the work done by the field in this circuit, when the small charge goes from point A and returns to point A after having passed through the closed circuit, this work must be zero. But this work must be zero. So the total work done when the small charge delta Q moves around the circuit is zero. We know that. But we can use our knowledge about the work produced on each separate element of this scheme. So when that small charge goes through the resistor R, what work will be produced? The potential difference on the resistor R, that is the potential difference between points A and B, which is here. The work produced on this element will be the potential difference times the charge which moves here. And then the work produced on this small resistor will also be a potential difference on the small resistor R times the small charge which moves through the small resistor. And then what is the work produced inside the battery when the small charge moves from negative to positive contact inside the battery? Whatever the construction, whatever the principle of operation of this battery, the small charge will always move against the forces of external electric field. If this is a small positive charge, it will be repulsed from the positive contact and it will be attracted to the negative part, negative contact. So when the positive charge delta Q moves here inside it, it will move against the forces of electric field acting on the charge inside it. So we will have to produce this work. An external actor will produce this work to move the small positive charge through the battery inside it. And this external work may be produced either by chemical reaction, if this is a chemical cell, or it may be produced by magnetic fields if we have a magnetic electric generator based on magnetic interactions and Lorentz forces inside and ampere forces inside the magnetic engine, inside the electric engine. Or this additional work and additional energy may be obtained, may be taken from the energy of photons, of light quanta which are absorbed here, if this is a sun battery, for example. So in different sources of voltage, there is always some external battery, external energy which is absorbed here and which should be conveyed in order to generate electrical current. And this external force will move the positive charge from one connector of the battery to another connector, and the external work will be produced against the forces of field. And it means that the forces of field are directed against the motion, against the direction of the motion of this charge. And it means that if the forces are directed against, opposite to displacement, then the field, electric field in this case, will produce negative work. Negative because the force is opposite to displacement. The displacement of the charge is to the left and the force is directed to the right. So on this element inside the battery, the work produced by electric field will be negative, and it will be equal to the potential difference on the battery, or the electromotive force of the battery, which I will denote by, well, let it be simply character E. So the electromotive force, which is measured in volts, electromotive force of the battery times this charge, and that must be zero. Yes, I have already written that due to the law of conservation of energy, that must be zero. And this is the work of electric field produced on the first resistance, external resistance, capital R. And this is the work of electric field produced on the internal resistance of the battery. And this is the work of electric field inside the battery. And all this must be zero, due to the law of conservation of energy. So, if this is zero, we can cancel delta Q and obtain this equation, that potential difference on the external resistance UAB will be equal, from this equation, that will be equal to electromotive force of the battery minus potential difference on the internal resistance of the battery. And that will be the electromotive force minus, what is the external potential difference on this resistor? Well, that will be the current, due to usual Ohm's law, that will be the current strength times the resistance. That will be the current strength times the internal resistance. So we obtain, in this way, the law, the Ohm's law. I will take this part and this part of the equation, and we obtain in this way that the potential difference, well, let it be in this way, potential difference between points A and B equals the electromotive force of the battery minus the current flowing through the battery and internal resistance of the battery. What is the UAB? That is the voltage on the contacts of the battery. On the contacts, these are the external contacts of the battery. And the voltage on the potential difference, which is on the battery, will be defined by this equation. That is the electromotive force of the battery minus something which depends on the current and the internal resistance of the battery. Suppose we have broken this circuit, suppose we have disconnected this switch so that the current is zero, no current is flowing here. This part will be zero. In this case, the potential difference on the contacts of the electric battery, the potential difference will be just equal to the electromotive force, that is the EMF, the electromotive force of the battery, of the generator, of electric generator. So the EMF is just the potential difference on the contacts of the battery in case the battery is not connected to external circuit. The battery is not connected, it's disconnected from the external circuit. Then the potential difference or the voltage on the contacts of the battery will define the electromotive force of the battery. In case the battery is connected to an external force, if we switch on this key here and connect this contact, then there will be a current flowing here in the battery. And then this formula will give us that the voltage on the battery contact will be less than the electromotive force of the battery, and it will be the voltage on the battery contacts will depend on the current and internal resistance of the battery. And while the current is certainly depends on the external resistance. If we take into account this external resistance here, then from this equation we can easily find the current which will flow in this circuit. That will be the electromotive force defined by the external resistance plus the internal resistance. That is also a form of the Ohm's law for a closed circuit. That is also a Ohm's law for a closed circuit. And this formula shows that the current in the circuit is defined not only by the external resistance in the circuit, but also by the internal resistance of the battery, and certainly by the electromotive force of the battery. So that is the portion of theoretical material which I wanted to present to you now, today. And another thing which I would like to discuss, is it possible to show this part of the blackboard? Okay. Another thing I would like to discuss is the energy of electric field. So let's consider a capacitor which is charged so that here is plus and minus, here is on this plate, on the left plate we have some plus Q charge on the left plate, and the right plate bears some negative charge. There will be an electric field inside, and the lines of electric field will be parallel and will fill the volume of the capacitor C, let it be the capacitor C, capacitor with capacitance C, and there will be such an electric field inside it. Electric field is also denoted by character E, just like the electromotive force in the our previous discussion, but it's obvious that these are absolutely different things. Here, this was an electromotive force which is measured in volts. This is a voltage of the battery, and here, this is the electric field strength, which is not the voltage. It has different units of measurement. Okay, but we consider another issue, which is energy of a charged capacitor. So, by definition of capacitance, we know that the charge of the capacitor is proportional to the potential difference U on the capacitor, the potential difference between the plates, and the coefficient of proportionality is called the capacitance of the capacitor. The charge is proportional to U, and U is proportional to charge. The larger the charge of the capacitor, the larger will be the potential difference between the plates. So if we consider the dependence of potential difference U and the charge of the capacitor, then it's obvious that when the charge is zero, and the potential difference is also zero, and the larger the charge, the larger the potential difference, and the dependence will be shown by a direct line on this graph. The larger the charge of the capacitor, the larger the potential difference. If we have some charge like capital Q, there will be some potential difference which corresponds to this charge, which is U. So if having charged capacitor and the charge Q on its plates, we decide to increase the charge of the capacitor and increase the potential difference, what should we do? We should take some small positive charge from the left plate and move it to the right plate in order to increase the charge. No, certainly not. We have to take, for example, some more electrons from the positive plate and move them to the negative plate. So the negative charge will go to the right plate to increase its negative charge. And if we take some small negative charge delta Q from the left plate, then its positive charge will be increased. In this way, we can increase the charge of the capacitor and increase the potential difference. If we take some charge here and move it to the right-hand side plate. If we do so, there will be a force acting on the negative charge. The negative charge will be attracted to the positively charged plate and will be repelled by the negatively charged plate. So we will move this charge against the forces of electrical field. It means if we want really to move some charge here, we will have to produce work, external work against the forces of electric field. If we produce work in order to increase the charge of the capacitor, it means that the energy of the capacitor will be increased. The potential energy of the capacitor will be increased by some external agent which produces this work to increase the charge of the capacitor. So if we increase the charge of the capacitor by some small amount delta Q, which is here, then the work produced against the forces of field, will be, by definition, a potential difference times delta Q. This is the definition of potential difference. Potential difference is defined through the work produced when a small charge delta Q is moved in the electrical field. But what is this potential difference times delta Q? this is a small area of such a rectangular figure. That is the work delta A, the area of this thin rectangle. That is the work produced if we increase the charge of the capacitor by a small amount delta Q. But we may ask a question, what work is required to increase the charge of capacitor from 0 to this large quantity, capital Q? Obviously, it will be the work needed to charge the capacitor from 0 will be given by the area of this figure. So the total work produced for charging the capacitor will be given by the area of this triangle, and the area of triangle will be given by the product of its legs, that is capital Q times potential difference, final potential difference divided by 2. That is the work, that is the area of this right triangle. One leg of triangle times another leg of triangle over 2. That is just a geometrical formula. Well, that is the work, and that will be the energy of the charged capacitor, because this work is produced in order to charge the capacitor, that in order to increase its potential energy. All the work done will go into potential energy of the charged capacitor. And this energy may be released, actually, if we short circuit the plate of the capacitor, then this energy will be released. But as the capacitor is charged, this energy is stored in the capacitor, because in order to charge the capacitor, we have to perform this amount of work. Well, by using this formula connecting the charge of the capacitor and the potential difference, we may easily derive that the potential energy of the charged capacitor, well, along with this formula Q times potential difference over 2, we may use other formulas if we recall that the charge of the capacitor is related to the potential difference and the capacitance C. Then we will obtain here Cu squared over 2. That is, if we substitute for Q its formula through the capacitance. Also, we may substitute the expression for U from this formula, and U will be equal to Q divided by C. So from here we will obtain Q squared divided by 2 capacitance. All these are different presentations, different expressions for the energy of the charged capacitor. For the energy of the charged capacitor. The charged capacitor has some potential energy which may be released later if we short circuit the plates by some wire. If we connect the plates, then some current will flow here and the wire will be heated because of this current, and heat energy will be released because some potential energy was stored in the charged capacitor, and in order to store some potential energy, we have to charge the capacitor, and for this purpose we have to produce work by external field. That is the simple reasoning behind this derivation. So, if we recall that the capacitance depends on some quantities like the electrical constant, the dielectric constant of the medium which fills the capacitor, the area of the capacitor plates, and the distance between the capacitor plates, then we will easily see that the capacitance is directly proportional to the dielectric constant of the medium which fills the capacitor. The capacitance is directly proportional to the dielectric constant of the medium. It means that if we fill this capacitor with some dielectric, having dielectric permeability epsilon, then what will change here? Under different conditions, the energy will change in different way. Suppose we have a separate capacitor which is not connected to outside sources. Then the charge of the capacitor will remain constant. It cannot be lost anywhere. The charge is constant. In this way, the energy will change just like 1 divided by C. And if C is proportional to dielectric permeability, then in this case, the energy of capacitor will be inversely proportional to dielectric permeability because of this formula. The dielectric permeability is proportional to the capacitance. That is why the energy will be inversely proportional to capacitance, to electric permeability of dielectric medium filling the capacitor. That is in case the charge is constant, the constant quantity in the denominator of this formula. And the charge will be constant if the capacitor is disconnected from the external circuit. Well, there may be a different situation when the capacitor is connected to some external circuit and, for example, is connected to some voltage source in such a way that the voltage on the capacitor will remain constant, will remain unchanged. In this case, if the voltage is remained constant, then the energy will be proportional to the capacitance, and in this case, the energy of the capacitor will be proportional to dielectric permeability of the medium filling the space between the plates. So the energy may depend in different way. The energy of the charged capacitor may depend differently for a separate capacitor disconnected from all other circuits, or a capacitor connected to an external voltage source, and the capacitor, or external voltage source, which gives a constant voltage U, a constant voltage. And in this case, if we insert a dielectric medium here inside the capacitor, if we insert some dielectric slab between the plates of the capacitor, the voltage will remain the same. And if the voltage is the same, then we have to use this formula. Voltage is the same, and the energy will change just like the capacitance. And the capacitance will be proportional to dielectric permeability. And so if we insert some dielectric slab here, the energy will increase proportionally to epsilon, the dielectric permeability. But certainly we can use this formula, but the charge will change in this case. Not only the capacitance, but also the charge in the capacitor will change. And it will be more difficult to analyze this formula. That is why I use for analysis the simplest formula, where only one quantity is changing and another quantity is constant. That is the simplest way. Though certainly capacitor can be analyzed using any formula. So, for example, this one, and you will have to take into account that both capacitance changes and the charge of the capacitor changes. And the result will be the same, so that in this case, when the capacitor is connected to an external source, voltage source, then the voltage on the capacitor is constant, and then the energy of the capacitor will be proportional to dielectric permeability of the medium. And for a separate capacitor which is disconnected from an external circuits, the situation will be different. The energy will depend in a different way. The energy of capacitor will change quite differently. By the way, it means that if we insert a dielectric slab here into the capacitor, the energy will be reduced because epsilon is larger than unity. If we insert here, the energy of the capacitor will be reduced. And it means that the capacitor performs some work while the dielectric slab is shifted into it, is moved inside the capacitor. The capacitor will perform some work because its energy will be reduced. And it means that the capacitor will help us move the slab here, because if it produces some work, then there will be a force of interaction between the capacitor plates and the dielectric slab, and this force will be directed in such a way as to absorb this plate, as to pull it inside the capacitor. And in this case, the situation will be different. When we insert the dielectric slab, the energy will be increased, and the work produced will be, the work needed to increase the energy will be done partly by the voltage source, by the battery connected to the capacitor. So that is shortly what I wanted to tell you about the energy of the charged capacitor. Well, I understand we have run out of time, and from this point let us finish this lecture.